You are about to spend a few dozen minutes of your life on the billions of other worlds that surround us. The universe thanks you for it. As I speak these words, the detection of about 5,630 exoplanets has been confirmed. That is, planets orbiting stars other than our own. And on average, a new one is discovered every week. But these thousands of new worlds are only the tip of a much larger set that we are going to explore today. To summarize 3 decades of remarkable discoveries in about 20 minutes, let's begin by assessing the situation. Starting from an astonishing observation. At first glance, almost all of these thousands of new worlds hardly resemble anything we find around us. Hundreds of planetary systems actually host gas giants of a completely different type than those found in our solar system. Today, we know of planets with masses comparable to Jupiter, orbiting dozens of times closer to their star than Mercury is to the Sun. Some of these scorching monsters, called hot Jupiters, are so close to their star that they take only a few days, sometimes just a few hours, to complete an orbit. While it takes Jupiter nearly 12 of our years to complete a single orbit around the Sun. Strangely, while it's estimated that barely 1% of Sun-like stars have hot Jupiters orbiting around them, these exoplanets were the first to be discovered. Because they're massive and close to their stars, they're the easiest to identify. We could spend hours exploring the amazing features of these worlds, subjected to absolutely hellish conditions. And some of them seem to have swelled up, giving these planets truly gigantic sizes, while others seem to be gradually stripped of part of their gaseous envelope. The lightest ones are affected by the power of the irradiation coming from their star, to the point where they end up surrounded by gigantic clouds of hydrogen, sometimes taking on the appearance of a planetary tail. Most of the time, these hot Jupiters are so close to their star that they have ended up being gravitationally synchronized, so that the solid core, buried under the thick gas mantle, rotates on itself in the same amount of time it takes to orbit their sun. Kepler-13b, an ultra-hot gas giant, 9 times more massive than Jupiter and orbiting 10 times closer to its star than Mercury is to our Sun, is most likely in this situation. This planet has estimated temperatures of 2,700 ding on its sunlit side. On the other side, in eternal darkness, the temperature plummets to only 1,300 Daxi. In itself, the discovery of the existence of these giants, which must be swept by winds reaching several thousand kilometers per hour given their temperature, is already quite an event. But perhaps an even greater surprise came from the discovery of a vast population of planets that was completely unknown to us. A population that has shaken up what we thought we knew about the frontier, separating the rocky planets from those made mostly of gas, and which we have tried to describe using the terms super-Earth and Mini-Neptune. To really grasp the strangeness of these worlds, let's take a moment to look at those in our solar system, which are shown here, respecting their respective size scales. If we compare the mass of these planets with each other, we notice a huge disparity between the rocky planets and the gas giants. The ice giants, Uranus and Neptune, are roughly 4 times larger than Earth in diameter and 15 times more massive. Meanwhile, Saturn and Jupiter weigh in at 95 times and 320 times more than our planet, respectively. Now, imagine that around nearly 1 out of every 2 stars we observe, there is a type of planet whose range of mass and size doesn't match anything that exists in our solar system. These planets can be 1.5 to 3 times larger and 2 to 10 times heavier than ours. They are a kind of intermediate between rocky planets like Earth and icy gas giants like Uranus and Neptune. That's why they're called super-Earths or mini-Neptunes. But what exactly do these worlds look like? Well, that's where it gets really complicated. Because depending on the history and dynamic characteristics of the gas and dust disks surrounding young stars, the planets that form there can end up being very different in nature. In fact, what you need to understand here is that planets with a mass ranging from about half to 15 times that of Earth are all made up of 3 ingredients. In varying proportions, molecular hydrogen, water ice, and a mixture of rocks and metal at their core, Uranus and Neptune, for example, are like this in terms of mass. They are roughly composed of 1/3 rocks and metal concentrated at the center, 1/3 high-pressure ice, and 1/3 a layer of hydrogen and helium. Whereas Earth is made up almost entirely of rocks and metal, with just a hint of a few volatile gases, including water. But within these new types of planets, many other proportions are possible, Some, in addition to having a metallic core covered with rocks, could, for example, contain 10, 100, maybe 1,000 times more water than Earth. Additionally, the planet may have a varying envelope of hydrogen and helium captured during its formation on top of the water. And the more massive this atmosphere is, the more likely we are to have a planet like Neptune. To sum up, there is almost certainly a continuum of composition with great diversity between planets dominated by rock and those dominated by gas. And if we add to the equation the type of star, the size and shape of the orbit, and the planet's rotation, then the range of possibilities becomes truly dizzying. To understand this, consider some specific examples. Here's an artist's view of 55 Cancri, a planet twice as large and nearly 8 times more massive than Earth, orbiting a star with a similar power to ours, 60 times nearer to the Sun than Earth. Because of this astonishing proximity, 55 Cancri is therefore gravitationally synchronized with its star, always showing it the same face. It has been estimated that the average density of this infernal planet is probably close to that of a cannonball, which leads us to say that it is made up mostly of rocks and metals. The surface temperature is 2,300 degrees C on the side constantly exposed to the star and a milder 1,300 degrees C on the side in eternal night. It is generally estimated that on the day side, half of the planet is covered by a single ocean of magma. 2,300 degrees Celsius is still a temperature nearly twice as high as that of the lava emitted by volcanoes such as those in Hawaii or Reunion. On the other hand, some exoplanets that have been discovered are so cold and so far from their star that it is possible that even their atmosphere, if they ever had one, ended up completely freezing, settling on the ground, and solidifying. That's the case with, I'll let you pronounce its name in your head, a world that is twice as far from the faint little red dwarf it orbits as we are from our own star, from the Sun, and whose surface temperature is estimated to be just under 120 degrees below zero, which is about the same temperature as Pluto, except that this planet has a mass about 5 times that of Earth. Perhaps even more interesting is the very likely existence between the rocky surface planets and the smaller gas-releasing ones of a number of fascinating intermediates, among which we find the still hypothetical but very credible ocean planets. These worlds, whose existence is strongly suspected, could contain very large amounts of water, because H2O, mostly in the form of ice, is one of the most common components in the clouds of gas and dust that give birth to the stellar system. Once again, it depends on their size, composition, history, and distance from their star. These ocean planets could be on the surface, entirely covered with ice, sheltering oceans several hundred kilometers deep. Or they could be enveloped in an atmosphere rich in water vapor, so thick and heavy that the liquid water on the surface can reach considerable temperatures without starting to boil. This is what we call a sauna planet. Acting like the lid of a pressure cooker, the atmosphere would pressurize the underlying ocean, allowing the water to remain in a liquid state even well above 100 degrees. In short, the main thing to remember here is that these fascinating new types of planets, the super-Earths or mini-Neptunes, represent a fantastic field of possibilities to explore. Apart from these peculiar planet types, we have found worlds that could be more exotic, unusual, or immense, with diverse orbital configurations, close, elongated, or eccentric. We have also discovered planets so massive, up to 13 times heavier than Jupiter, that it's hard to even consider them as planets, because these are so heavy that they approach the lower limit of what we call brown dwarfs. These objects are so massive that nuclear fusion has begun in their cores. Very special, but still too light to truly shine and thus be considered full-fledged stars. We have also detected planets whose surface temperature is higher than that of many stars, such as Kelt 9b, an ultra-hot Jupiter that orbits a monstrous blue giant star, a star much larger and more massive than our Sun, with a surface temperature nearly twice as high. And it will turn into a supernova and explode in a few million years. Kelt 9b is therefore probably a planet that, on a cosmic timescale, is about to disappear. We've even discovered worlds orbiting one of the strangest objects that the forces of nature are capable of forming. A millisecond pulsar, a rapidly spinning neutron star, making thousands of rotations every minute. The fact that some of these objects, only about 10 kilometers in diameter, and containing more matter compressed inside them than in our Sun, have planets raises immense questions. Because for an object like this to form, a star had to die in a cataclysmic explosion. The question is whether planets orbiting these strange stars, which pierce the night with X-ray and radio wave bursts, with the regularity of a metronome, are the remnants, the leftovers of ancient planets, maybe the exposed cores of former gas giants whose outer layers were blown away by the explosion. In that case, a similar fate may be awaiting Kelton 9b. But it's also possible that these worlds formed later from the material ejected by the explosion of the star, and are, in a way, a second generation of planets born from the ashes of a system that has now disappeared. We don't know for sure yet. I could also have told you about the hypothetical planets made mostly of carbon, or about the discovery of hot Jupiters, whose retrograde orbits move in the opposite direction of their star. We could continue adding to this list for a long time. And don't think that all these newly discovered planets are alone. Many belong to multiple planetary systems, meaning they have several planets orbiting the same star. We know of almost 900 multiple planetary systems, including 659 with 2 planets, 151 with 350, with 425, with 59, with 6, and 1 with 7. And we've even been able to identify a star with 8 planets. In itself, finding groups of planets orbiting around the same star is not particularly surprising. That's the case with our Sun, for example. And many of the systems in which we've identified only one planet must actually contain several more that our telescopes haven't been able to detect. And then, more than the number of planets evolving within multiple systems, what really surprised us were the architectures of their orbits. Because, in the vast majority of cases, these planets form kinds of miniature solar systems around small stars called red dwarfs. We regularly find 5, 6, sometimes up to 7 planets whose orbits are so compact and close together that they could all easily fit between Mercury and the Sun. Alongside these stars with multiple planets, we've also discovered many planets that have multiple stars. About 200 planets have been identified in binary systems, with 35 in triple systems and 3 in quadruple systems. Kepler 16b exemplifies this well. This gas giant, with the mass of Saturn, was discovered orbiting around 2 stars that themselves revolve around each other. If Kepler 16b has exomoons, even the tiniest elevation must cast a shadow. 2 shadows in a landscape with 2 suns rising and setting, creating an atmosphere worthy of the best science fiction movies. And since the 2 solar disks of the stars aren't the same size, the smaller one must occasionally be eclipsed by its companion. Within the Gliese 667 System 3 stars coexist, engaged in a strange dance together. 2 of them, close together, form a pair, the center of gravity of the system, and around them orbits a 3rd star, which itself is accompanied by 7 planets. One of these 7 planets, due to its supposed mass and temperature, could very well have the characteristics of a total desert-class super-Earth. Here, it is depicted as extremely hot and inhospitable, with average surface temperatures of over 150 degrees. A world completely dry and scorched, with an atmosphere perhaps bathed in the light of 3 suns. 1 primary scarlet sun and 2 smaller distant secondary suns. A world where nights must be rare. Within triple star systems, several configurations are actually possible. If in the one we just flew over, it's the pair that leads the dance, in others you can find 2 small stars orbiting around each other. And this pair itself orbits around a single star, but a much more massive one, the true centerpiece and core of the system. For all the planets evolving within these multiple systems, the sunsets must echo each other in a never-ending dance, changing throughout the year, depending on the position of the planet in its orbit and the stars in relation to each other. For us who have only one sun, multiple systems may seem exceptional. Yet binary systems are more than common in our galaxy, where more than half of the stars are in pairs. Perhaps even stranger than those planets with multiple stars, some simply have none at all. They're called rogue planets. These are worlds without stars that drift alone in space. We don't know yet if these wandering planets formed within planetary systems before being ejected from them, or if they were born independently of stars. For their part, in any case, we've been able to identify a few hundred of these wandering planets within stellar nurseries. All of them are massive gas giants, young and therefore incredibly hot on the surface. And since these are extremely difficult to detect without the spotlight of stars to reveal them, we think their number must be very high in our galaxy. Okay, let's summarize these observations numerically. At the time I'm writing this, we've been able to identify about 400 planets that are comparable in size to Earth, or smaller. Almost 2,000 are found in the continuum, spanning from super-Earths to mini-Neptunes. 700 are about the size of Neptune, and 2,000 have masses that exceed those of Jupiter. Taking into account the limitations of our detection methods, it turns out that planets are more abundant the lower their mass, as our planetary formation models predict, by the way. And generally speaking, many of them have a very small orbit. Thus, 75% of the exoplanets discovered are closer to their star than Mercury is to the Sun. And that's a huge surprise. Before we started harvesting new worlds, no one imagined that such planets could be common in the cosmos. Yet, it is now estimated that if you randomly pick a star in the sky similar to the Sun, you have a 50% chance that it hosts a planet larger than Earth on an orbit closer than Mercury's. It was also discovered that nearly 1/6 of Sun-like stars host gas giants, with a mass ranging from 1/3 to 10 times Jupiter's. Or, if you prefer, from 100 to nearly 3,000 times the mass of Earth. And more than half of the systems, of all types combined, also seem to have at least one Neptune-type planet, meaning a planet with a mass 10 to 30 times that of our planet. There are also the intriguing super-Earths and mini-Neptunes. It is now estimated that 1 out of every 2 stars has a planet larger than Earth and smaller than Neptune. And in most cases, we don't know whether these are dominated by rock or by volatile elements. In short, the diversity of these worlds far exceeds what we expected to find. Many even have such strange features that few researchers, or even science fiction writers, would have considered them credible just a few decades ago. And the craziest thing about all this is that this abundance of diversity is obvious through our telescopes. While our current detection methods still have many blind spots, we only ever find what we are able to detect. If all the planetary systems in our galaxy were like our solar system, we probably wouldn't have detected any of them. Because our instruments are only able to detect planets much more massive than Earth, or orbiting extremely close to their star. And so, many planets that are too small, too far away, or simply poorly oriented still escape our detection. In other words, if we haven't yet discovered any system with an architecture and planets similar to ours, it's simply because we're not capable of doing so yet. Now here is a fascinating animation that, by itself, practically sums up everything I just told you. Here, you have 726 different planetary systems represented, containing 1,815 exoplanets. And this represents nearly a third of all those we have discovered. In these systems, stars are omitted because they would be too large to display. On the other hand, the sizes of the planets are more or less to scale, and their color gives us an indication of their surface temperature. To compare all these planetary systems with ours, Ethan Cruz placed the sizes of the orbits of the planets in our solar system at the center of this animation. And here, you can see, represented by dotted lines, the sizes of the orbits of Mercury, Venus, Earth, and Mars. There you can see Jupiter's, here Saturn's, and there Uranus's. And you can see, amazed, that all these newly discovered planetary systems are so tightly packed around their stars that they would all easily fit inside Uranus's orbit. 5,630 discoveries made using all detection methods. That might seem like a small number compared to the roughly 300 billion stars in our galaxy, but it's actually already a lot. Because from these thousands of discoveries, we are able to estimate the total number of worlds existing in the Milky Way. Let me give you a concrete example. You'll see, it's fascinating. To detect the presence of exoplanets, the Kepler Space Telescope used the transit method, which means it analyzed the light coming from stars, to try to spot the disturbances caused by the passage of a planet. The problem with this detection method is that it only allows us to find planets that are large enough to block a significant portion of their star. Furthermore, other planetary systems lack a privileged cosmic orientation. So Kepler was only able to show us the tip of the iceberg. And it's estimated that only 1% of the systems we observe are oriented in relation to us, in such a way that their planet passes precisely in front of their star. In other words, 99% of planets can't be seen by detection methods that try to spot their shadow. The great thing here is that since we know the extent of our ignorance, we're able to quantify the limits of our detection methods. For example, today we're basically only able to detect large planets or those very close to their star. And by taking into account all the gaps in our net and the tiny portions of the sky we've managed to observe so far, we're able to estimate the underlying population of planets that are currently slipping under our radar. The verdict is as follows. If you gaze into the cosmos and let your eyes wander, practically every star you're looking at likely has one or more planets. More precisely, it's estimated that there is an average of 1.4 planets per star, but this number could be much higher. On our galaxy scale, this small average becomes an immense number. The most conservative estimates are around 200 to 300 billion planets, while others put the number closer to 500 billion. Knowing that these numbers, already staggering, are certainly underestimated, since they don't take into account the planets that are in the blind spots of our telescopes, such as those with low mass or those that are too far from their star. And for which, since we can't detect them, we have virtually no data. So much so that some estimates put this number at around 2 trillion worlds in our galaxy alone. I don't know about you, but when numbers like that are thrown around, I quickly lose track. And rather than just summing it all up by saying there are a lot, I suggest we try to find a visual way to represent all the planets in our galaxy. To truly grasp the astronomically huge scale, let's cautiously estimate there are around 300 billion of them. Imagine that, if you could magically turn all those planets into little marbles with a 1 centimeter radius and gather them all in one place. Then you would have enough to fill about 100 Olympic-sized swimming pools to the brim. If you devoted a page to each of those planets and described 300 per book, you would need to write in order to mention them all. 65 times more books than are contained in the entire National Library of France. Even if you spent only 1 second per page, it would take 8,500 years to skim through them all. Okay, there are a huge number of them. And each of these worlds has its own history, its own colors, its own climate, its own chemical composition. In this vast field of possibilities, this giant bag of marbles, a large majority of planets have terribly hostile characteristics. Those that are too far from their star and have solid surfaces are probably completely frozen, while many of those that are too close would probably make hell look like a little piece of paradise. But between these two extremes, between fire and ice, there is a happy medium, a region of space that surrounds each star and that we usually call the habitable zone. And where the conditions are, at least on paper, favorable for moderately sized planets to have liquid water on their surface. From there, by limiting ourselves to planets that maintain a suitable distance from their star, avoiding extreme temperatures, on the surface, we can have fun roughly estimating the number of worlds that could potentially harbor life. By considering only the small red stars, which account for nearly 80% of those in our galaxy, and around which we find Earth-like planets in the habitable zone, in 10 to 30% of cases, we already end up with 20 to 70 billion potentially hospitable planets. As for stars like our Sun, it is believed that at least 10% of them have an Earth-sized planet in their habitable zone. Given that our galaxy has about 30 billion of these stars, we end up with at least 3 billion Earth-mass planets orbiting in the habitable zone. This estimate suggests there may be stars similar to our Sun, since it's very difficult for us, with our current technology, to detect planets with masses comparable to Earth when they're not orbiting very close to their stars. And of course, we can imagine that conditions favorable to the development of life exist outside these zones. For example, planets that are frozen on the surface can still maintain liquid oceans deep below thanks only to the energy stored during their formation. But the thing to remember here is that there are now tens of billions of worlds whose orbits are located in the habitable zone of their star. So of course, being in a zone where water can be in a liquid state doesn't mean that you'll actually find any there. Mars, located in the solar system's habitable zone, has an extremely dry surface. Habitable doesn't mean inhabited, but you get the idea. It's absolutely mind-blowing. In just a few decades, the plurality of worlds has become a reality. We are the first generation in all of human history to witness the discovery of thousands of new planets in real time. It's even possible today to contribute to these discoveries from your own backyard. Because as long as you have quality amateur astronomical equipment, you can help refine our knowledge of the timing of hot Jupiter transits. As baffling as they are, all these worlds reflect our own condition and raise big questions. Frank, a big thank you for your valuable help in writing this episode, and also for agreeing to let me take, let's say, a few shortcuts. Is there an idea you'd like to revisit? Something that fascinates you, makes you wonder, or that isn't often highlighted?
Yes, there's one point that particularly interests me, which is that we often ask the question of life elsewhere in the following terms. Are we alone in the universe? That's a nice question, but of course what really interests us is the answer. And what I find very important to point out is that we will have an answer to this question. Or what if life is very abundant in the universe, meaning abundant enough to populate planets in our immediate galactic neighborhood? To illustrate, if we are very optimistic about the evolution of our observation capabilities, we can hope that in a few decades we'll be able to analyze the atmosphere of around 100 Earth-sized and Earth-temperature exoplanets among the closest ones. And that corresponds to the exploration of a region about 100 light years around the Sun, and that represents only 1/25,000th of the stars in our galaxy. In other words, statistically, for us to make this discovery, our galaxy must have at least 25,000 inhabited planets. And not just inhabited though, there have to be 25,000 planets in the biosphere so that are inhabited, but whose biosphere has profoundly changed the observable properties of the planet so that we can be able to identify the presence of life. So now what if we assume that life is less abundant than that? For example, if we only find 100 of these inhabited planets with observable signs of life in each galaxy in the universe in our own, that still makes 100 trillion inhabited planets in the universe. So we wouldn't be alone at all, but we would be far from being able to know it, to discover it. So today's science itself can tell us is life outside of Earth so rare that it can only be found in a few galaxies beyond the observable universe? Or on the contrary, is it so abundant that it populates stars in our own neighborhood? The only thing it tells us is that if life is rare, it's not due to a lack of planets.
It's mind-blowing.
Yes, I think so too.
And the universe thanks you for dedicating a few dozen minutes of your life to the hundreds of billions of worlds that surround us. Remember to turn on the bell to stay updated on upcoming releases, or follow me on Insta for some behind the scenes of the project.